Okay, let's get started. So, are there any questions? What is due today? Good. So, any questions? So, I put an announcement every Friday until the end of the semester. I'll have my Friday office hours official now in addition to my Wednesday office hours. So I know some people can't make the Wednesday one, but can make the Friday one, so I figure it's good for those people. But any questions? And if you haven't picked up your test, please pick up your test 3. Okay, so on Halloween, we were talking about something really scary, pointers. So the things that we were talking about with pointers are passing them as function parameters, that sort of thing. And then we ended with if we wanted to make the pointer constant so it can't point to any other place that it was initially assigned to, or I can just say, well, the pointer, whatever it's pointing to, that thing will not change. But the location of the pointer can change. But it's just the thing that it's initially pointing to is not going to change. Or you can do both simultaneously, which is what we saw here, which is I don't want the pointer to change locations, but I also don't want the value at the location to change either. Okay, so let's just continue from there. So one of the things that I mentioned was this stack versus heap allocation, right? So does anyone remember what the difference is between the stack and heap allocation? At a high level, yeah.
So like the stack is like it's all the constants. It's like just held in place in memory that they don't.
No, that's good. So the stack is mainly used for passing parameters, for holding local variables, or also determining where in the function you are, things like that. So if we allocated things on the stack, so the stack grows down, or it grows in one direction, and then if we need to come back to something above, maybe we exited the function somehow, we need to take all those things off the stack to get back to where we were. For the heap, the good thing about that is it avoids this need to go back so far in the stack, because if I allocated it somewhere else in the heap, then I only need to store the pointer on the stack, which is a lot cheaper than to, say, put in a whole array on the stack. So basically the rest of the pointer slides are about dynamic memory allocation, which is heap allocation. So the way we do dynamic memory allocation is to use this new operator. So I just want to warn you about this. Please don't use new if you can. And we'll see ways of how to avoid it. But I know you'll be seeing new many times if you keep programming C++, so you will come across this, so you might as well know about it. So what this does is it allocates, in this case, a double on the heap, not the stack. And then on the stack, it keeps the pointer to wherever that is in the heap. And we can't necessarily guarantee where in memory this is, but it's dynamically allocated. So the good thing about dynamic memory allocation, if you remember one of the previous labs where I asked you to get an integer from the user, let's just say like this, and then let's just try to make an array with n elements from the user. So let's just make an array of n elements. I don't know why that works. So This did not work for some people. Does anyone know why? Yeah. No, an integer array, like a native array. Yeah.
Is it because arrays need to have a specific constant for their size?
Yeah. So the size of this array, so this array is allocated on the stack. So in order for the stack to know, okay, how much am I going to allocate on the stack, because there's no pointer involved here, it needs to know at compile time, hey, how many things are going to be in this array? Does the compiler, is the compiler able to figure out how big n is here at compile time? No, because it's entered by the user at runtime. So I don't know why this actually works, but for some people this didn't work because of that reason. So we needed instead to allocate the array on the heap because it's dynamically allocated at runtime, not at compile time. So if we instead do something like this, where we say the array either as a pointer or, actually you do need a pointer here. So if I want to make an integer array on the heap with n elements, I need to say new int n like this. So here I'm saying I'm going to make an integer, the thing's a pointer, but we know it's going to be an array. So this is going to point to the start of the array. And new means allocate it on the heap, dynamically allocate it. And I'm going to have an integer array on the heap with n elements. And so this works exactly as expected. There's nothing technically wrong with doing this. So you can allocate things on the stack or on the heap. In some cases, you have to allocate them on the heap, but you can do one or the other. It depends on the actual use case. And we'll go into we kind of talked about the use cases, but we'll go into why new is useful and what are the pitfalls of using new. Okay, but I can allocate anything I want on the heap or on the stack, but sometimes you have to use the heap. So here's an example of something very similar to what I just showed as an example. So I have two pointers up here. Count is a pointer, array putter is a pointer. So I'm going to initialize count. So is count going to be on the heap or is it on the stack? Count itself. So it depends on your perspective. The pointer itself, where's the pointer allocated? On the stack. Where's the value initialized in? The heap. So when I say count is equal to new int, the pointer is on the stack, but the value of where it's being pointed to, that is on the heap, yeah.
So what if I'm going to put around the stack and the heap, so that way, because the stack is generally faster than the stack.
That's technically true, yes. It'd be faster if you have a very few things on the stack versus the heap, but you do need something on the stack because that's where the CPU is looking to say, okay, what am I going to do next? I allocate things on the stack that way. It doesn't look into the heap until it sees something in the stack that says, okay, look at this memory address via this pointer. But the CPU doesn't immediately look into the heap unless it sees something in the stack telling it to do so. So like a pointer, for example. Okay, so I allocate the pointer count on the stack, but the value is in the heap. I print how many students, cin, so I cin to count. What if I remove the star on the cin part? What would that do instead? Putting the star there because count is a pointer, star count is the value that is the value initialized in count. But what if I remove the star? Yeah. Right, I'd be setting the address instead. But I figured the number of students shouldn't affect the address of a variable, right? So here we have to put star count because we're entering a value. I want to modify the value of where the count is located, which is on the heap in this case. So here I'm going to make the array putter, which is a pointer. So am I initializing this pointer on the stack or the heap? The array pointer. So is the pointer on the stack or the heap? Stack. Where's the array initialized? On the heap. Right. So I'm going to make a new, because we say new here. New int, and then star count. So is star count the address of count or the value in count? The value in count. So I'm going to make an array with that many students. And then here I'm going to say, I'm going to loop this many times. I'm going to enter the score. And then I'm going to see into the array at index I. By the way, does anyone see what is wrong with this example? This example works, but is there anything that we can make simpler? Well, we have to use the heap for the array, right? Because we don't know the size of the array at compile time. We have to enter the value at runtime. But think of the pointer here. Do I need a pointer here for count? No, because there's nothing that I need the address of count here. So in fact, I could remove the star on all the instances of count, and it'll make the program easier and faster, actually, because I don't have to reference the value in count on the heap. Everything I need is right on the stack, where I'm already so far. So in fact, I don't need the pointer for count. I do need it for array putter in this case. Any questions about this, though? Okay. But if we initialize some memory on the heap, since it's not on the stack, when the program exits, it frees up all the memory on the stack. But if it frees up everything on the stack, and the only thing pointing to something in the heap was on the stack, and we remove that, the compiler is not responsible for freeing all the heap memory that we allocate. Okay? So we have to say ourselves, delete some variable. So if we delete something on the stack, we need to actually at some point say delete this variable. Or in the case of an array, we say delete square bracket the array name. So if we go to here, and then if we make this array right here, and actually let's do the example here. And then I don't like the star on count, so I'm going to actually remove that. Oh, by the way, this doesn't compile because when you say new, it returns to you the address of where this is in memory. And since count is not a pointer anymore, we don't need to actually say this. So if we do cin count like this, and then I think that this program is a lot easier to read without all the stars on count here. But anyway, so what things have I initialized on the heap in this example? What variables? Yeah, array putter is allocated on the heap, and how do you know? Well, it's a pointer, but that doesn't necessarily prove that it's on the heap. A pointer can still be on the stack. Well, the pointers are always on the stack, but the value could also be in the stack.
The keyword new.
Right, because I called new here, that initializes it on the heap. Okay, well, is the compiler responsible for freeing up heap memory? No, so are we responsible for freeing up the heap memory? Yes. So what do I call to free up heap memory? And it ain't Ghostbusters here. So, actually, free would work, but that's the C style way of doing it. What is the C++ way of doing it? Delete. And in this case, is it an array that I'm deleting or just a single value? It's an array because array putter is pointing to an array in this case. So here I would have to say delete with the square brackets of array putter. And then that's what we would need to do. Okay? Any questions about how new and delete work? Yeah.
So it says only use delete with dynamic memory.
Yeah.
What's the situation where it would be a bad idea to use delete?
It's never a bad idea to use delete. But there's nothing wrong with using delete, but what if down here, after I said delete, I accessed array putter? Bad things can happen for that. But even going past that, let's just say that I do this delete down here, and I definitely don't access array putter after that. So there's nothing wrong there. What if we did this? If we checked if array putter I is less than 0, and then what was our usual way of dealing with values that are not good? Like if they entered an invalid value, what is the way that we've been doing it so far? Well, I mean, we could do a while loop to ask them repeatedly to do it, but before we even did that, what did we do? It returned 0. Good. Anyone see anything wrong with doing that?
It doesn't ever get to delete.
Ah, right. So if I return 0 here, that exits the function and never hits the delete statement. So that is something what is called a dangling pointer. So maybe that's the next slide, I'm not sure. Actually it is. I didn't even know that. It was a good segue. So if you don't get to the corresponding delete statement of something, then you'll have a dangling pointer, which means that the pointer is freed. The pointer is all gone, but all of the memory still exists in the heap, and you didn't call delete on it. And since there's no pointer anymore pointing to that place, there's no way that you can guarantee that you'll be able to free that memory. And so, fortunately, most of the time when you stop your program or the program stops, the operating system is going to clean up that memory for you anyway, but you can't guarantee that actually is going to happen. And the other thing is, if we look back at this example, and I try to access array putter down here, then of course bad things can happen, as I said. So the way you usually deal with this is setting the array pointer, or any pointer for that matter, to null putter. Oops, not numeric limits, null pointer. So what does this do? So what does the delete statement actually do? Just the delete statement. Yeah, it frees up the corresponding heap memory. But what about the pointer? Is it still there? Just the pointer. Yeah, the pointer's still there. But since we freed up that heap memory, this shouldn't point to anywhere that we need it to point to anyway. So here we're saying array putter, we're going to set to null putter. And here it technically says the value is never used, which is true because I'm not accessing array putter after that anyway, but it's a good idea to set your pointers to null putter once you delete something. Okay, so let's, I'm not sure if this, oh, okay, that'd be too hard to find. So think about vector, for example. So what does vector have on the back end? How is like the contents of a vector stored on the back end? Just an array, right? And are the contents in a vector stack allocated or heap allocated? Can you imagine? They're heap allocated. So does a vector necessarily need to know how many elements it has at compile time? I'll get to you in a second. No, it doesn't know at compile time how many things it's going to have. So it has heap allocation. You got a question?
What is the difference between a stack allocation and a heap allocation?
So I talked about this last time. So a stack allocation is when you do not say new, and a heap allocation is when you do say new. And when you do say new, you have to have a pointer for that because you need something on the stack to point to the heap memory. Yeah.
How are they functionally different?
Well, what do you mean by functionally different?
Why would you use one instead of the other?
Right. So why would I use a heap memory versus stack memory? If I allocate a giant array, if I put that all into the stack, then if I need to access something like I'm returning from the function, I have to release all of that stack memory unnecessarily to get back to something because the stack grows on one side only. But if I allocated it in the heap, then I only have a pointer that's stored there and it's faster that way. Okay. Let's see, what was I trying to do? Okay, yeah. So let's get back to dangling pointers. So try not to have dangling pointers, and I'll show you ways of avoiding that and memory leaks. So yeah, so I don't really like this solution down here. It says like a memory leak occurs, blah, 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 blah. The solution is free up the dynamic memory, but that's kind of the problem, right? Because if we go back to the example, then you can imagine that we have multiple exit paths from any function. If we allocate something on the heap, then I could exit here, I can exit here. It may be possible that at runtime, I'm going to do a division by zero error, or I'm accessing something past the end of a vector, causing some unexpected crash of the program to happen. And so we would need to be able to handle when that happens, we need to be able to free the memory. But it seems like there are so many possible ways of being able to free something up, to delete the memory in the heap, that it just seems way too difficult to be able to say, oh, put a delete here, 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 here. Because it's just we need to reason about every possible way we could be going through our program. So we'll be seeing a way to fix that, which is a lot better. Yeah, so that's dangling pointers and memory leaks. You could return a pointer if you want to. There are reasons why you could, if you, in the case, you actually do need the pointer return, but I've never used it, so it's just something sparingly to use. But you can return it if you want to. Yeah. Usually, if you dynamically allocate something, you have to return a pointer anyway, because if you want access to that data later anyway. So if you dynamically allocate something in a function, return the pointer or free up the memory, whatever the case may be. Yeah, so about memory leaks, if you use a new, you have to use a corresponding delete. If I allocate two variables on the heap, both of them with new, I have to delete both of them, okay? Yeah. So here's the really interesting bit right here, this second bullet point. It says, if a class needs dynamic memory, like vector, for example, what you should do is allocate the dynamic memory in the constructor using new, and then deallocate with delete in the destructor. So remember, the destructor is the thing with the tilde on the front. Why is it like this? Why should we do it this way? Yeah.
Because it sets terms for our constructors and destructors?
It sets the what?
It sets the terms, like it sets up keywords to more readability for the program.
Well, if we're using the class, like not even looking at the implementation, then we wouldn't even know about it anyway, but you're right. It seems like the right place to put the new and delete because in the constructor, we're constructing the object, and so we need to initialize any memory we might need. And then in the destructor, we're trying to remove any memory we had in the object, and that's where the delete should happen. But why does this solve the problem of every new needs a corresponding delete? Think about it for a second. Go ahead.
Is it because the objects are stacked, and so in the CD freezes the stack of the objects, it will call the structure?
Exactly. So think about this. So let's suppose instead of int right here, we had some defined type with a constructor and destructor. When I return 0 this way or return 0 this way, what of the object is called? When I'm exiting the function, what is called on the object? The destructor. So no matter what path we exit the function, the destructor is called. So if we put the delete of the object in the destructor, then no matter how we exit this function, then we free up that memory. Which is why for vector, we never had to use delete, because internally it has the heap allocation in the constructor and the corresponding delete in the destructor. Interesting. So this is something, I'll put it in a text file. It's actually a very interesting concept and very, very important in C++, something called RAII. Anyone know what RAII happens to stand for? I don't expect you to know, but yeah. This is not random access, but good idea. It's actually called resource acquisition is initialization. So the main idea behind, so I don't think this is in the slides, it might be. The idea behind here is wrap up the new and deletes in stack allocated objects. So let's just say we have a student object, or maybe an ASU object, which has, for example, an array of all the students that it has. And we allocate that array on the heap. So for the student object, we're going to initialize it on the stack. So the object itself is on the stack, but internally it has a pointer which points to the heap. And then in the constructor, we put the heap allocation in the constructor and the corresponding deletes in the destructor. So this is just a blanket term to say, wrap up any heap allocation that you use into a stack allocated object. You shouldn't have to use new and delete in, like, say, the main function. Wrap it up into an object that is allocated on the stack and let the object, the lifetime of that object, handle the heap allocation for you. So the lifetime of the object means when you declare it in, like, the main function, it's constructed, and then whenever the function exits, no matter how that happens, the object is deallocated, it calls its destructor. So it's just a wrapper for heap allocation is all that really is for. Any questions on RAII or new and delete, that sort of thing? Okay, let's see. So let's get back to here. You could, just like with ints, like before, you could have a pointer to a class object. Nothing special with that, actually. Yeah, so, but if you want to actually do something with the value in the pointer, you need to do a dereference just like before. And then put parentheses around it because of the way that operators work, but you need to put parentheses here if you're going to use a pointer with an object like this. But this kind of violates RAII because, as I said, we're allocating things on the stack. We don't need pointers for the object itself. The object may have pointers internally, but the object shouldn't have pointers. Maybe you do need it, but it depends on the actual use case. Most of the time you don't. But sometimes if you don't want to do the dereference parentheses then the dot to access some function or some variable, we can use the right arrow. It means exactly the same thing. So if you have a pointer to an object, you use the right arrow instead of dereference and the dot, but they do exactly the same thing. Okay. Dynamic memory for objects. Sometimes you may need this, but most of the time you shouldn't need it. But in those cases, you can call new on the type of the object just like before, nothing new there. You can pass values into the constructor with parentheses as the case may be, and then call delete on it. It works exactly the same. There's nothing new here. Let's see. So this is what I was kind of saying earlier. So are structs the same as classes? Just as a refresher. They're not exactly the same. Anyone know the difference? Right. So structs are public by default, classes are private by default, but they are exactly the same otherwise. So you can think of this like a class, for example. So this list object, so the object is a list, but it itself has a pointer to some heap memory, for example. So when you're working with the object, you don't have to think of the heap memory that's being allocated. You just work with the object itself, which is one of the nice things about object-oriented programming. You don't have to think about that sort of thing. Yeah, so the way that you access something in a object pointer here is right arrow just means it's just the same thing as doing a dereference parentheses with a dot after it. Yeah, so here if you do a star on the front, this accesses the value at that place, and then this one's very similar. Yeah, it's very similar, but okay. But if you really, really need a pointer, which does happen, you do actually need a pointer sometimes. So, and you can't wrap it up in another object and let the objects handle it for you with RAII. You do actually need a pointer sometimes. But we saw it was dangerous to have a pointer because there could be multiple exit paths from a function, and then you need to put the corresponding delete in every one of those places. So a smart pointer is basically a very tiny wrapper around a pointer. So it behaves exactly the same thing as a pointer, but it handles RAII for you. So you don't have to make a new object and wrap the pointer up for yourself. The smart pointers, starting in a recent version of C++, do all the work for you. So it fixes all of the issues about dangling pointers, memory leaks, and then something interesting called double deletion, which is, remember, we can assign the address of a pointer to a different pointer, so you can have two different pointers pointing to the same thing. So if this one calls delete on the value here, what do you think this one's going to be pointing to? The deleted memory, and that is a bad thing that can happen, which is double deletion here. So smart pointers are a way of handling all of these, but you can still get the flexibility of having a pointer. So smart pointers are, they're just an object. There's nothing special about them, but they work like a pointer. Yeah, so they can automatically delete dynamic memory that's no longer being used, and we'll actually see how that actually works. So there were 3 types of pointers in C++. This third one, the slides originally had it as okay, but I actually crossed it out because this one's actually deprecated, I believe. So, or it's actually very dangerous for other reasons. So the 2 that you should focus on are unique putter and shared putter. So just from the names of them, what do you think unique putter is doing? What is the purpose of unique putter? So unique putter just says, here's something in the heap that I want to have something point to it. A unique putter says, okay, I'm the only one that's pointing to this thing. There's no other object pointing to this, okay? So if this thing calls delete, this pointer calls delete, then this thing won't have anything else being pointed to it, okay? A shared putter is where you can have multiple things pointing to the same object. And then you may be thinking, okay, you just railed on why that's a bad idea because one can call delete and the other one might not. But there's actually a nice fix for this that shared putter does nicely. So let's get into unique putter first. Okay, so a smart pointer for both cases is able to handle the memory that is allocated on the heap for you. Okay, so the smart pointer behaves like a normal stack allocated object. So when you create the smart pointer, it heap allocates the memory as necessary. And then when the function exits or the smart pointer's destructor is called, the corresponding memory is deleted. In the case of unique putter, but we'll see the difference with shared putter in a bit. So a unique pointer points to some object, and there is only what is called one owner here. So there's only one owner of this object. So the pointer itself is called an owner. Okay? If we want a unique putter, then you should expect that there's only one thing pointing to the object. So that may be a good thing in some circumstances. You don't want multiple things pointing to the same location. But you can transfer the ownership of a unique putter to a different unique putter. So if this thing is a unique putter for this memory address, then I can reassign the pointer to go to some other pointer to this object, and then I can't use the original one anymore. So that may be good in some circumstances, like if I'm returning from a function, I had a unique putter up here, but then I'm using a unique putter as the result, then I may need to reassign as necessary. So when the pointer goes out of scope, or if it takes the ownership of a different object, the destructor is called as necessary. So here's an example. So we need to include a different header for this, but aside from that, it kind of looks almost the same thing as vector. So here we just say unique putter, angle brackets int. So this thing is pointing to some int. So effectively it's doing the same thing as int star. And then the name of the thing is uputter in this case. And then I'm doing the dynamic allocation in the constructor. So the constructor of unique putter is going to get the pointer of where this int is allocated on the heap, so that internally it can handle that pointer as necessary. But the nice thing about uputter is it overloaded the star operator. So in fact, I can look at the address of this putter, or I can look at the value by calling the dereference operator. It works exactly the same thing as a normal pointer, which is really nice. So if you really need a pointer, use unique putter because it's guaranteed to work if you have multiple ways of exiting a function. But if I want to transfer ownership to a different unique putter, I have to call this very important function. Maybe we'll talk more about it later, but this function called move. So intuitively, this move means take the guts out of this unique putter and then transfer it, all the guts of it into this other unique putter. Okay? That's not exactly what happens, but it's a good analog of what actually happens. So at this point, when I call move on uputter, I shouldn't be able to use uputter at any other point. And then uputter2 is going to have the same data as uputter did before. So I can transfer ownership as necessary for a unique pointer, which is kind of cool. But I added this slide. This was not in the slides before. But there's a better way to call to make a unique putter. So if we look back here, notice that I call new in here. So for reasons that I won't go into, it's a good idea to try to avoid using new yourself, okay? So you could do this, but it's just that there are pitfalls associated with it. So the better way of making a unique pointer is to call this special function in this version of C++ that's more recent, called make unique, okay? So make unique is going to internally going to call the new operator for you. So you don't have to do it yourself and then risk having some issues happening with that. So I would recommend using make unique over just making a unique pointer. And then the cool thing is that uputter is a unique pointer. It works exactly the same as before. So I say, why is it better than the previous example? Because you're not calling new yourself. That's the main reason for it. Okay, any questions on, I'll get to all of unique putter first. So if we want to do the ownership transfer thing, I have to call move on the putter. Yeah, so any object owned by uputter2 is deallocated because remember, this is a unique pointer. It's pointing to exactly one thing. So if uputter2 is pointing to somewhere else, then that thing has to be deallocated in order for it to point to this new thing right here. And then uputter becomes empty, as you might expect. Yeah. So what is this move function? So it's required because of how move actually works. Yeah. So the move function basically just does some magic, I'll call it, to take the internals of whatever object it's looking at and then move it over to something else. So the great thing about move is, suppose that I think of string, for example, or vector. Suppose I have a string right here or a vector, and I have another one over here, and I want to take the contents of it and then move it over to here. What is the way that we've been doing it so far? Well, the way we've been doing it is, think of vector. I'm going to look at each of the elements in this vector, and I'm going to push back into this vector, okay? What happens at the end when I do that? If I do a pushback of everything from here into here, don't I have two copies of the same thing? So that's something that is really annoying about C++ sometimes. It likes to copy objects too much. If I want to take the contents of this and move them over to here, why should I have a copy of the original? So that's one of the main motivations behind move, because if we have something over here, we want to move it over to here, why should I have to do a copy? Why don't we just directly move it over? So that's what move is really useful for. I won't go into the details because it's really complicated how it works. But you shouldn't have to do this, but if you want to clear a unique pointer, you should just let it go out of scope. But if you want to clear it yourself, then you can do equals no putter or a special function called reset on the unique putter. But you shouldn't have to do this for any smart pointer, let alone a unique pointer. Unique putter, you could, instead of putting a type here, you can put an array with a type if you wanted to. The cool thing is that it'll call the square bracket delete for arrays versus the normal delete. But so it'll do the right thing, but it's just, remember, make unique is better than calling a unique pointer with a new here for the reasons I've said before. Any questions on unique putter? So what is the overarching idea behind unique putter? Can anyone tell me? Yeah. Right. So it's uniquely pointing to something else, and for that thing in the heap memory, nothing else is being pointed to it. Good. So, but sometimes we want multiple owners of an object. So remember, Smart Pointer manages the data that's associated with it. But a shared pointer is a way of having multiple pointers to the same object. Okay, so maybe you want to have a pointer over here and a pointer over here pointing to the same thing in memory. Sometimes you do want that. Yeah, so how does this better than just assigning a normal pointer to another pointer and then I have two things going to the same object? So what happens in a shared pointer here is it keeps what is called a reference count. So it just says, okay, when I make this shared pointer, how many things right when I make it are pointing to this data? Right at the beginning. Just one, right? And so it keeps that reference count of 1 at that point. If I have something else and I say, okay, you can also point to this thing via this shared pointer, then the reference count goes up to 2. But what if, for example, okay, we have these two things pointing to this object, and let's say this one goes out of scope. So this one's maybe the function exited, but this one is still alive. What happens on the internals of shared pointer, do you think? The reference count is going to go down to 1. So the cool thing here is that now we can manage how many things are pointing to this object. What happens if this reference counter is now decremented to 0? What will actually happen? Then we can delete the data, because now we can ensure nothing's pointing to it. And so we won't have a dangling pointer anymore. So that's one of the nice things about shared pointer. So I could make a raw pointer if I wanted to, or just pass new int, and it works. The way you make it is identical or analogous to unique pointer, but you call shared pointer instead. And then we can create a second shared pointer and then pass it over. And then by doing this, the reference count will go up by 1. So all of these pointers are controlled in what's called the control block, and that handles the reference count for you. So here, there's a corresponding function which I definitely recommend called make shared. So like make unique, make shared is your best friend here. So all references to the object are tracked in this control block. So here if we make 2 shared pointers, there's gonna, so there's some pitfalls here. We'll talk more about them on Monday. But any questions otherwise? Great, I'll see you all on Monday.